Hello and welcome to 2.3 Projectile Motion. And this is the end of Unit 1. So this is really the culmination of some of the things that we've looked at, and especially 2D motion. This is sort of a unique two-dimensional motion problem. So we're talking about projectile motion, which you can see some pictures below. It's the idea is we've got some sort of projectile or some object that's going horizontally and also falling towards the ground, like this. So different projectiles, they're like throwing a ball, that sort of thing. So a projectile is an object that moves on a curved path due to gravity. And basically is falling towards the ground as it moves. So the interesting thing about projectile motion is that when we're doing these problems, the horizontal motion, and so that's in the x dimension, and the vertical, which is in the y dimension, they're completely separate. Or we say they're independent. Now, if you remember from last lesson, we said that same thing for river crossing problems. We said the horizontal motion and the vertical motion are separate, they're independent, but the difference between these two is that for river crossing, both of the velocities are constant. So you're going across the river at a straight speed, and the river is pulling you downstream at a constant speed. But here for projectiles, the vertical motion has acceleration. And this is the acceleration due to gravity. And so that makes for some interesting problems. There's one term that's important here that we haven't looked at before. It's called the range. And the range is just the x displacement. So you know what the x displacement is, you know what that means, but we give it a name called the range. And so this is how far it goes horizontally. And often we want to know that answer. Like if I'm throwing a ball, I want to know how far it goes before it hits the ground. We call that the range. And for these problems, we need to use a certain convention here to make our problems easier. So the convention is that we use positive for the directions up and right, and we use negative for down and left. Now that's the convention we've been using sort of all along, but we're just going to make sure we're using those conventions. It makes our lives easier for these problems. Okay, so there's a couple pictures of this motion. You can see here we have some sort of ball being thrown out a window. And what you should notice is that that ball is moving at a constant speed or a constant velocity horizontally. It never increases. It's just going along in that direction. But the vertical speed is increasing, and it starts pretty much at 0, and then it picks up a bit of speed, more, and that's what causes it to have this arced path. And that's coming from the vertical acceleration. We've got another picture over here, and you can see that if we drop two balls, one of the balls is dropped and the other one sort of is launched with a certain horizontal speed, you can see that these dots all line up. So it means that doesn't matter whether the ball is moving horizontally or not, they'll still fall at the same speed. And we've talked about that in class a bit. The vertical acceleration is the same, so you can see that after any amount of time, they always end up at the same vertical position, even though this one is also moving horizontally. And that's just to reinforce the vertical and the horizontal are independent. Whatever these balls are doing vertically, it's completely separate from the fact that this one is also moving horizontally. Okay. We'll go to our first problem and give that a try. This says a beanbag is thrown from a window 10 meters above the ground with an initial horizontal velocity of 3 meters per second. There's a picture here. We're throwing a ball. We throw it straight out, and it's going to fall towards the ground. How long will it take the beanbag to reach the ground, which means what is its time of flight? So I just want to know how long it takes to go from here to here. And it's exactly the same as saying how long would it take to fall straight down. It's the same amount of time. The fact that it's going horizontally as well doesn't change the vertical component. So for this problem, I'm just going to focus entirely on y. So I'm just going to say I'm only interested in the y dimension. So if I'm looking in y, the initial velocity in the y dimension is 0. Even though we're told that we have an initial velocity of 3, that was horizontal. There's no vertical component at the start. So our initial velocity is 0 meters per second in the y. My delta d is negative 10 meters. I'm going down 10 meters. And my acceleration is down 9.8. And this is what I'm talking about with these conventions. I'm not writing directions, I'm just using positive and negative to indicate direction. Okay. Now this negative 9.8 is that can sometimes confuse people. We need that negative in there to say that we're going downwards. Okay, and now we can use our equation. Delta d is equal to vi delta t plus 1/2 a delta t squared. And our initial velocity is 0, so that makes things nice and easy. I rearrange for delta t. The square root of 2 delta d over a. And now I can just solve this. We've got negative 20 over negative 9.8. This gives me 1.4 seconds. Done. Part B. How far will the beanbag travel horizontally? Which means, what is its range? Well, now, horizontally, I don't care about the vertical anymore, so I can just say I'm only looking at x. We just found in the previous problem that delta t is equal to 1.4 seconds. And we know that the x velocity is 3.0 meters per second. Remember, we're ignoring the vertical now. Horizontally, it's moving at a constant speed. So that means delta d is equal to v delta t, and I can plug in my numbers. 3.0 times 1.4. This gives me 4.2 meters. And you see that that's actually very straightforward. Not difficult math at all. Even though the problems seem like they could be complicated, the math is very clean. Alright. So that was still an object that just launched horizontally with no angle. But now we're going to look at what if we launch an object on some angle. So now it has some vertical component to its initial speed. So we'll see how that changes things. This says a soccer player running on a level playing field kicks a soccer ball with a velocity of 9.4 meters per second at an angle of 40 degrees above the horizontal. So this is 40 degrees here. Determine the soccer ball's time of flight. That's going to be the first part here. So, time of flight. It's going to go up and back down. That's the same as saying it's going to go up and back down. If I just look at the vertical, up and back down. I don't need to worry about the horizontal for this at all. I just need to find the time for it to go up and back down. So I'm going to focus on y. I can say that my acceleration is negative 9.8 meters per second squared. And delta d, my displacement. Well, it starts here, it goes up, goes back down, it ends at exactly the same spot. That means the displacement is 0. 0 meters. Good. And now the last thing I want is my initial velocity, VI. Well, this is going to take a bit of math here. So we said that I am launching my soccer ball at 9.4 meters per second at this angle of 40 degrees. So I'm going to break this up here into my components. And now I need to get a vertical component and a horizontal component. You can see that I have VIY and I have VIX. So my VIY, and I'll just put VIY here, this is equal to 9.4 sine 40 degrees. And that gives me 6.042 meters per second. I'm keeping lots of extra digits on that for now. Okay, and now I can use some formulas here. I have A, delta D, VI. I want delta T. So I can say delta D is equal to, and this is the same equation that we saw before, VI delta T plus 1/2 A delta T squared. All right, now, unfortunately, VI isn't 0 anymore, so I'm going to need to do some different math. But what I do have is that delta D is 0. So 0 equals 6.042 times delta T plus 1/2 times negative 9.8 delta T squared. Now I'm trying to solve for delta T. So what I can do here is I can factor delta T out. So I can say that 0 equals delta T times now 6.042 minus, so 1/2 times 9.8, we've got minus 4.9 delta T. So now I factor this, and this tells me that delta T equals 0, or, now I just want to solve here. For this to be equal to 0, either this is 0 or this is 0. And so for that second one here, we're saying that 6.042 minus 4.9 delta T equals 0. I can rearrange that to solve for what delta T would have to be here. So I can say delta T is equal to 6.042 divided by 4.9, which gives me 1.233 seconds. Now, notice the first one was delta T equals 0. That makes sense, because this ball started at that position at time 0. It went up and back down. When it comes back down, this is our second time, this 1.233. So we can say, therefore, the time of flight is 1.2 seconds. Now we want the range. Well, range, remember, we're just looking at the x dimension. I have now my time of flight. And this is usually how it goes, is if you're trying to find the range, generally first you need to find how long it's been in the air, which you do from the y dimension. And then we can apply that to the x. So I have this. I can say that my Vx is equal to, well, we need to look up again at this picture that we had, this picture up here. So I can say Vx, the x velocity here, is equal to 9.4 cosine 40 degrees. And I'm just going to leave that as it is. I'll put my equation here, delta D, I want to get the range. This is equal to V delta T. And I can put in some numbers here. 9.4 cosine 40 times 1.233. This gives me 8.879 meters, which rounds nicely. We can say, therefore, the range is 8.9 meters. Good. Now finally, C, we want the maximum height. And this is new. We didn't look at this in the previous problem because in the previous problem it started at its maximum height and just got lower. But now we're going to talk about where does it reach that maximum height. So we've got some arc that looks like this. And the question is, how high is that maximum height? Well, the way I'm going to find that, at that point, you can see that vertically, this thing is moving faster, 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 and then it's getting slower and slower and slower to the point where at this maximum point here, the vertical speed is 0 because it starts falling back down again. So I'm going up, 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 up. Now I've stopped going up, and now I start going down. So this is where my y velocity is going to be 0. So I'm going to go back into my y dimension. I can say that my initial y velocity was, I have this from before, 6.042 meters per second. I can say that my acceleration is equal to negative 9.8 meters per second squared. And the new piece here, which we'll always be using for a problem that says something like maximum height is always at this top point of the parabola, which is always where our final velocity is 0 meters per second, vertically. Okay, now we can go ahead and do some equations with this. So Vf squared equals Vi squared plus 2a delta d. And then I'll rearrange that here. Delta d, because we want to find the vertical distance. This is equal to Vf squared minus Vi squared over 2a. And now we put in numbers. 0 squared minus 6.042 squared over 2 times negative 9.8. This gives me a value of 1.9 meters. Good. And, we should have a therefore. Therefore, the maximum height is 1.9 meters. Perfect. Okay, this last page, the same idea. It says it's a problem with a golfer. I am going to leave you to try doing this yourself, but I will warn you right now that it's going to be a bit more difficult. And I'll just fill out the starting point here, because we can say that delta dy, on the last one delta dy was going to be equal to 0. This one here, we're going down 30 meters in this problem. The problem is the same, except that we start and end at different locations, and it makes the problem a lot more difficult. So we've got delta dy is negative 30 meters, and still, well, I'll lay this up the way that we had it before. We say we're in the y dimension, delta d is equal to negative 30 meters. The acceleration is equal to negative 9.8 meters per second squared. And VIY equals, well, that's where we're going to have to, again, break up our velocity. We've got our velocity is 25 meters per second at an angle of 50 degrees. So that means our VIY is going to be this guy here, 25 sine 50 degrees. Okay. From there, to get this this delta t here, we can say the same equation here, delta d equals vi delta t plus 1/2 a delta t squared. But this is where the problem comes in, because I'll just fill in a few numbers here, and then I'll leave you to think about this yourselves. Because we get here delta d, negative 30, is equal to 25 sine 50 degrees. Actually, I'm just going to give that 25 sine 50 degrees an actual value. So up here, this is equal to 19.6 19.151 meters per second. Okay, so we can say 19.151 delta t plus 1/2 times negative 9.8 delta t squared. Okay, and when you look at this problem, you can see this is a quadratic problem. So you're going to need to use the quadratic formula to find the roots, to find delta t. So I can write this as 0 equals, we have negative 4.9 delta t squared plus 19.151 delta t plus 30. Then you're going to use your quadratic formula, which says that delta t is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Hopefully you remember that formula from grade 10 math. Okay, so you're going to use this, you fill in all your values, and that will lead you to an answer. I'm going to leave you to do that, but you can see how that adds an extra level of difficulty to this problem. Okay, and we will look at that together in class as well. So I will wish you luck on that one, and I'll see you in the next